AS Paper 2, Lesson 1, Kinetics. The study of kinetics is how a change in conditions affects the rate or speed of a chemical reaction. So remember, the speed of a reaction, the faster it goes, the quicker or less time it takes. So the speed of a reaction is inversely proportional, opposite to the time taken. Think about if you run a race. If you run a race really quickly, you do it in a small time, a short time. If the rate or the speed when you're running a race is slow, then you take a long time. So something that takes a long time is going slowly. Something that takes a short time is going quickly. And kinetics is the study of rate, also known as speed of a reaction. A reaction can only occur when collisions, that means that particles bump into each other, take place between particles having sufficient energy. So they need to bump or collide into each other, but they also need sufficient energy. If they've not got sufficient energy, they just bounce or collide off each other without a reaction taking place. The energy that's required for a reaction to take place, the minimum, the smallest amount of energy required, is called the activation energy. Therefore, when particles collide or bump into each other, if they have the activation energy, or above, then they have sufficient energy and a reaction will occur. Maxwell-Boltzmann distribution. These were two chemists that drew a graph that looks like this. Up the y-axis, number of molecules, and along the bottom, the x-axis, is the energy. So if you look at this curve, if I took a sample of gas, then a sample of gas has a distribution curve like this. Let's have a look what it tells you. How many particles have no energy? So if I go back right down to zero energy here, then the line goes through 0, 0. So zero number of particles have zero energy. How many particles have zero energy? None. That's why it goes through 0, 0. How many particles have a very high energy? So if I trace it up here, up to this top point here, does it touch the x-axis? And the answer is no, because even at a very, very high energy, there are some particles, not many, but there's a small number of particles that have a very high energy. The area underneath the curve represents the total number of molecules in the sample, usually a gas. So the area underneath the curve represents the total number of molecules or total number of particles in the sample. Mark on the graph the energy that most particles have. So most particles have at the peak there. So if I trace the peak down, it would cross the energy, the x-axis, around about here. So draw a line down, and this point directly down from the peak is the energy that most particles have, around about here. The mean energy is slightly to the right. So if you go from the peak slightly to the right, just a little bit to the right, around about here, and trace it down, then the mean energy is somewhere around about here, just to the right. Redraw the curve at a higher temperature and explain what you have done. You've got a space here to do it, and then we've got to redraw the curve at a lower temperature. Explain what you have done. So let's do the higher temperature first. No particles have no energy, so we're going to start there at 0, 0. And at a higher temperature, you'd expect that more particles have a very high energy, because the higher temperature provides more particles with more energy. So it starts here at 0, 0, and it goes to here, above the previous curve. So now when you draw a curve, you'd expect the peak to be further to the right, because more particles have more energy. So you're going from here, 0, 0, and you're producing a peak that's further to the right than this one. It's somewhere here. And the end of the line is above the other line here. However, there's an interesting point to note. The peak at a higher temperature is lower, so it comes up here to about here, not as high as the other peak, and then comes down and ends up higher than that line there. To try and explain that, no particles have no energy, that's why it goes through 0, 0. More particles have a high energy at the higher temperature, because the higher temperature provides particles with a higher energy. The peak is going to the right, so more particles, the number of the particles have the number of particles is shifted to the right, so the energy that most particles have, the peak is further to the right because more particles have a higher energy, but that peak is lower. And the reason that peak is lower is because if you've got the same sample of gas, you've got the same number of molecules. So if it comes from here and it's over here and higher over here, that peak must be lower here, further to the right and lower, so it comes here, so that the area underneath the curve remains the same, because the total number of particles remains the same. Redraw the curve at a lower temperature. Well, it goes through 0, 0, because no particles have zero energy. This time, the peak is going to be to the left, so it's going to be to the left of this previous peak, because at a lower temperature, less particles have energy. So at a lower temperature, particles have a lower energy on average. So that's going to go somewhere here. Now it's going to go higher than previously. Higher, and then down and lower than this other curve. And underneath, if you can squeeze it in, it will go underneath that curve. It won't touch the x-axis. It will go in between the previous curve and the x-axis without touching. So to go again, at a lower temperature, no particles have no energy. The peak is to the left of the other peak because particles have less energy. The peak is higher than the other peak, comes down, undercuts this other curve and squeezes between those two lines. So even at a low temperature, some particles still have some energy. The reason the peak is higher is because the area needs to stay the same, and if it's undercutting this here, that's why the peak goes higher, because the area underneath the curve must stay the same, because the total number of particles has stayed the same. The temperature has changed. What has not changed? The area underneath the curve has not changed because the total number of particles have stayed the same. What is the definition of activation energy? It's the minimum amount of energy for a reaction to happen. Draw a vertical line to represent activation energy. Now you can put that anywhere you want, but I would put it, let's say, about here. Let's draw a vertical line about here. And you should have three curves now. So you should have one at a high temperature, one at a lower temperature, and the original one. Put a line in the same place on each of the three curves around about here. So about 3/4 of the way along the x-axis, around about here. Shade on the graph the representation of the extra particles that have an EA at the higher temperature. So if you did all three curves on the same graph, at the higher temperature, if you had your line and at a higher temperature here, The particles underneath the graph to the right of the line have the activation energy, and the extra particles are the ones here above the original line and underneath the curve of the higher energy curve. Definition of the rate of a reaction. The rate of a reaction is the change of concentration of products with time. So if you're making a product, it's how much more of them you make. A concentration is a measure of how much there is in a given space. So the rate of change of concentration of products with time. So over a certain amount of time, how much more concentrated are the products? How much more products are you making? At a higher temperature, more particles have the activation energy, or the minimum amount of energy for a reaction to occur. We've already said that. Most collisions do not lead to a reaction because most particles do not have the activation energy. We've already said that. A small increase in temperature. So if you're talking about how to change the rate, well, changing concentration, that is the space that the particles are in, will lead to a greater rate because there's more chance of collisions. However, a small increase in temperature has a much better effect on the rate, a much higher effect on the rate, because more particles have the activation energy and more successful collisions within a given time. Think about people in a lift. If I put more people into a lift and increase the concentration in that lift, yes, they're going to jostle into each other and collide, but if we've not got the activation energy, that doesn't matter. So temperature is key. So concentration will increase the number of collisions and increase the rate, but temperature has a much higher effect because by increasing the temperature, then you've got particles with the required activation energy, and therefore you're going to get successful collisions. Effect of concentration and pressure. If you add water, lower the concentration, there are fewer successful collisions. That's because the water particles get in the way of the other particles colliding and the reaction decreases. If you increase the pressure, the particles are closer together. So if you increase pressure of a gas and push the particles closer together, there are more successful collisions, so the rate increases. But remember, temperature has the greatest effect because that affects activation energy. Catalysts. Catalysts work by providing an alternative reaction route. It means they can react and come together in a different way. A catalyst usually bonds the particles to the surface, brings them close together so that then they react, and then once they react, it releases them again. So a catalyst provides an alternative reaction route, so more particles have the activation energy, come together, and more particles have the energy required to react. A catalyst lowers the activation energy. A catalyst is often a thin layer on a support material such as ceramic. You only need the catalyst on the outside. Catalysts tend to be expensive, and it means that less catalyst is needed, and there's an increased surface area, so a greater proportion of the catalyst is on the surface, and it saves on cost. Now you've got some past papers to do, and you can see from screen the past papers that you've got to do. I'd like you to send the past papers in, either by post or dropping them off at the 11 to 16 site, or you can take some photographs and email them to me at rob.jones@sthelens.org.uk. I'd like you also to take some photographs of the graphs that you've drawn so I can check those and feedback as well.